Okay, so we just discussed how to calculate the pH of acids, and we've gone through examples of strong, weak, and polyprotic acids. So now we're going to get into how to calculate bases. How a base reaction is written, it's different than the acid reaction. There's two types of bases. There's the strong base and there's the weak base, just like in the acid case. Strong bases, we've discussed before, all they do is they dissociate completely to produce hydroxide in aqueous solution. So just like with strong acids, all you need to do is figure out how much hydroxide is in the strong base, and that's a pretty straightforward problem. Weak bases is a little bit more complex, so you actually have to write a reaction where the base is reacting with water. In this case, water is your acid, so the proton donor, and you form a conjugate acid and then hydroxide. Now, if you were to write the equilibrium constant for this expression, you'll get this here, and that is what we call the base ionization constant, or Kb. So this is really your analogous equilibrium constant to the Ka for acids. This table gives you some examples of weak bases and their Kb value on the left side. And then on the right two columns, you see the conjugate acid form of each of those weak bases. One thing I want to point out about the weak bases is how most of them are derivatives of ammonia, which is NH3. So if you look at many of the molecules here, they all have that NH with 3 bonds attached to the nitrogen, and that's the pattern of a lot of weak bases. And when I say derivatives, I just mean that they're compounds derived from ammonia. So it's possible that one of the H is replaced with a carbon or a carbon chain, and as a result they have different base strength. Just like in interpreting Ka values, the larger the Kb value, that means the stronger that particular base. So here we have stronger bases at the top and weaker bases at the bottom. The conjugate acid trend, of course, is the opposite. So stronger the base, the weaker its conjugate acid. Again, very similar to acids, because the Kb values is less than 1 in all of these cases for these weak bases. What we expect to see in solution is the base species itself, whereas the product is not going to be a whole lot. So in other words, if I have a solution of a weak base like ammonia, for example, what I would see is the base itself, the ammonia itself. The ammonium and hydroxide is actually going to be a much smaller concentration. So that's something you need to keep in mind as you're visualizing these reactions. For any acid-base equilibria that occurs in water, we have this relationship, which is the Kw relationship, right? Where the product of the hydronium concentration times the hydroxide concentration has to always equal 10 to the minus 14. And we can use this to derive an expression to help us solve the pH of base. And that is to just put negative log on both sides of that equation. So now negative log Kw, and then negative log of the expression on the right, which is the H3O plus times the OH minus. And of course, based on log properties, I can separate out to the negative log of just H3O plus and negative log of OH minus. But negative log of H3O plus, just the negative log of H plus, which is PA. Negative log of OH minus, we can call POH. Remember that that operator P just means negative log. At 25 Celsius, Kw is equal to 10 to the minus 14. So negative log of Kw is the same as negative log of 10 to the minus 14. And that value is just 14. So in other words, we can say that pH plus POH is equal to 14 at 25 Celsius. And that helps us calculate pH if we know POH, which we will when we solve base problems. So the steps that you will use to calculate pH of bases will be as follows. It pretty much mirrors what we did when we were calculating pH of acids, except that now we're focusing on hydroxide as the main ion. So we want to write all reactions that produce hydroxide. We want to rank those reactions from the largest to smallest K. If we're talking about weak bases, we're specifically interested in ranking the Kb value. And then once we solve the problem either using an ICE table, one of our assumption method, or quadratic formula or successive approximation, we can then go ahead and calculate our pH using that formula we just derived, where we can take 14 minus POH to calculate the pH. And lastly, just like with acid, you don't have to worry about reactions with small k, because usually the reaction with the largest K will be the one that determines the POH and therefore determines the pH of the entire solution. So let's do a couple of examples to show how this works. We're going to start with the pH of half a molar of NaOH. And it's helpful here to know what are the strong bases and what are the weak bases. So the strong bases are anything that is a soluble hydroxide salt. If you go back to Chem 11 solubility rules, you might remember that some of these hydroxide salts are soluble, and they're the ones that are bonded to group 1A cations, so sodium, potassium, lithium, etc. And then there's 3 from group 2 that you want to keep in mind, which is calcium hydroxide, strontium hydroxide, and barium hydroxide. So those 3 are the ones that are uniquely soluble enough to produce the hydroxide, and therefore it's a strong base. As I said earlier about strong bases, all you need to do is just quantify the hydroxide. So what happens with a soluble hydroxide salt like sodium hydroxide is it just dissociates completely to form sodium ion and hydroxide ion. You have a one-to-one stoichiometry between your salt and your ion. Your salt is half a molar, so your ion has to also be half a molar by the time the dissociation is complete. So then all you need to do is just take the POH, which is the negative log of 0.5, subtract that value from 14 to get the pH value of 13.7 for half a molar NaOH. Notice here that I don't write any other reaction, and of course this species is dissolved in water, so I'm ignoring the water autoionization, but we had spent, I think, enough time to convince ourselves that that is not really a relevant player in determining pH, as long as we're talking about concentrations that are much higher than 10 to the minus 7, and half a molar is much higher than that number. Let's take a look at the second problem, which is half a molar of ammonia. So ammonia is NH3 and it's a weak base. How do I know it's a weak base? First off, it's not one of those soluble hydroxide salt that I just mentioned. But also, if you look up the Kb table, you'll find that ammonia is listed there with its own Kb, 1.8 times 10 to the minus 5. So again, if the Kb is less than 1, that means it's a weak base. And so when you deal with a weak base reaction, you're going to have to write out the reaction just the same way as we did when we're working on weak acid problem. And what we have to write is the weak base reaction. That's the reaction I started this segment with, which is this reaction here at the top. So I want to make sure I write the base and then plus water, forming the conjugate acid and hydroxide. And that's what I have written here. My base is ammonia, and then I add water, form conjugate acid, and hydroxide. I started in my ice table with half a molar ammonia. I don't have any other products. It's minus x plus x plus x here because this is a weak base. So weak base, by definition, it's not completely going to convert into hydroxide. So we don't know how much that number is. We have to calculate. So at equilibrium, this is what we have. Now, the way we solve is just the same way as in the acids problem. Now we're going to set it up equal to Kb, that whole equilibrium expression, and then x squared over half minus x equals to that Kb value of 1.8 times 10 to the minus 5. I got that number from the Kb table. I made this small k assumption here, so I'm assuming that the half minus x is the same as a half, and then that gives me this value as my final answer. Anytime you make an assumption, you have to check, right? I checked it, it's fine, it's less than the 5%, so I'm going to go ahead and use that to help me calculate my pH. So pH is just 14 minus POH. My POH is negative log of the number I just got, 3 times 10 to the minus 3, so I end up getting a pH of 11.5. Just a conceptual idea here to note that the pH of a strong base and a weak base is pretty different, right? For the same concentration, which in this case, they're both half a molar, you see that the pH of the strong base is 13.7 and pH of the weak base, which we just calculated, is 11.5. So clearly that there's a difference in strength there, and the reason is because they don't produce the same quantity of OH minus. The strong base produce more, the weak base produce less. Now, what about polyprotic base? So polyprotic bases is just bases that are able to accept more than one proton. So just like in the case of acids, where you have polyprotic acids can donate more than one proton, bases can accept more than one proton, more than one hydrogen ion. The carbonate ion is an example. We would call it a diprotic base because it can in total accept 2 protons. And the reactions are shown here. So we start with carbonate reacting with water. Water donates a proton to carbonate, forming bicarbonate. And that has a Kb equals to 2.1 times 10 to the minus 4. And then that bicarbonate ion can then react with another water to form carbonic acid with a second Kb. You notice just like with the polyprotic acid, the difference between those two Kb values are pretty big. So that gives you an idea that when you're trying to calculate the pH of polyprotic base, a lot of times the first step of the proton acceptance is really the one that matters. The later steps, which has a much smaller Kb, will typically not influence the pH calculation. So here's a quick example on a problem with polyprotic base. In this case, we're dealing with a different diprotic base called quinine, which is an anti-malarial drug. The formula looks kind of complicated there, but I just want you to remember those structures of weak bases that are all derivatives of ammonia. So just keep in mind that that N, that nitrogen, can have 3 different bonds to it. So there's 4 lone pairs, and then each of these lone pairs here can possibly bond with something. So a lot of times you'll see a structure formula like this where you have N with 3 bonds. So sometimes all 3 lone pairs are being used to bond, sometimes only 2 of them are being used, sometimes only 1 of them is being used. So just keep that in mind in terms of looking at these weak base formula. So the quinine formula is C20H24O2N2. So that N is where that proton is going to bond with quinine to form the conjugate acid. But to make life a lot easier, you don't really have to even know how to draw that structure. It's irrelevant really to solving the problem. All you need to do is just represent the base as B with 2 lone pairs on it, because that will tell you that it can potentially accept 2 different protons, right? And you know that it's diprotic because they tell you in the question and they give you 2 Kb values. Okay, Kb1 is 10 to the minus 6, Kb2 is 10 to the minus 9.8. So we'll go ahead and solve the problem. First, we write this first proton acceptance step, which is the base plus water forming the first conjugate acid and hydroxide. The Kb is written there, 1 times 10 to the minus 6. I'm using the initial concentration that I was given, again, minus x plus x plus x because it's a weak base, and then I get my equilibrium expression. I use Kb1 here to solve, since this is the first step, and I made my small k assumption, and I solve for x, which gives me this number. I check my assumption right here, and it's less than 5%, so therefore I can go ahead and use that assumption as my answer. So the x is going to equal to 4 times 10 to the minus 5, which happens to be the same as the hydroxide ion concentration. And just to point out the analogy of this to the acid situation, typically once we have this, we would say that that second reaction can be ignored, okay? But I just want to prove to you that you can ignore it by actually doing the problem. So in the second reaction, you would start with the conjugate acid from the first step, which now becomes the base, which can accept another proton, right, from water, is forming now this species, right, BH2 plus. Okay, so there's 2 protons being accepted. The charge on it is now plus 2. And hydroxide. Kb2 will be used for calculation. Now, notice my initial concentration now is 4 times 10 to the minus 5 for the BH plus and the OH minus. Where do I get those numbers from? From the first step, because in the first step, I was solving for OH minus and BH plus, which is now appearing in this parts of the second reaction. So I just want to point out how I got those numbers. Other product, the last conjugate acid is still 0 because that's not produced yet. And then we now work out our ice table and we get these expressions at equilibrium. Using Kb2, I can write my equation out equals to 10 to the minus 9.8, which I can just rewrite as 1.58 times 10 to the minus 10. Going ahead and assuming with small k, I will get my x equals 1.58 times 10 to the minus 10 because, you know, basically the 2x here goes away, right, when it's being compared to that number. And so the 2 numbers cancel out, and then your x is just the value of the Kb2. And checking that, I find that my error is very, very small, much smaller than 5%, so clearly I'm okay here. Now, if I wanted to calculate my total OH minus concentration, I would use the OH minus from step 1 plus OH minus from step 2, ending up with 4 times 10 to the minus 5, which just is the same as the OH minus from step 1. So in other words, the step 2 is irrelevant. It's so small that it doesn't really make a difference. So pH is unaffected by the second reaction. Therefore, just like in the case of polyprotic acid, we can ignore additional dissociation step. We just need to worry about the step that has the largest K.